Commodities Portfolio Optimization. The example presents an investor's decision. A man wants to invest $200,000 on a portfolio of 4 different metal commodities: gold, silver, platinum, and palladium. His portfolio horizon is of 2 years. He has not decided towards which type of risk profile he should lean. Our objective is to present alternative portfolios that would optimize his choice on how to invest upon the 4 different commodities. The objective of this module is to show an example containing 2 powerful features of @risk, the time series tool and RiskOptimizer, its optimization tool. We will use time series analysis to forecast the future stochastic price of 4 different metal commodities 24 months upfront, considering historic price variations and the correlations between these assets. Then, we will use optimization techniques, using RiskOptimizer, in order to determine different portfolios. That is to say, combinations of assets that will comply with the investor's risk profile objectives. Time series and @risk. In the fields of statistics, economics, and mathematical finance, a time series is a sequence of observations, typically measured at regularly spaced times, such as every week, every month, or every quarter. We will use an example of commodity prices for metals. Other examples of time series are weekly currency exchange rates, the daily closing value of the Nasdaq Composite Index, and monthly crude oil prices or any other type of commodity. The @risk time series command provides 2 types of tools: 1. Fit and batch fit tools for fitting various time series processes to historical data, and then projecting these to the future. And 2. A defined tool for simulating data from a selected time series process for use in an @risk model. The time series results from such a simulation can be viewed with the normal @risk results options or by using the time series results window. The fit and batch fit commands are analogous, in a time series context, to the commands in @risk's distribution fitting with the same names. The define command is analogous, in a time series context, to @risk's define distributions command. Whereas distribution fitting and define distributions are relevant for individual probability distributions, the time series commands are relevant for time series processes. These time series commands add @risk functions to your spreadsheet model, just like the define distributions command. However, the @risk time series functions are array functions. They change the cells where your time series forecast is located as a group in each iteration of a simulation. The fitting procedure assumes that the time series is stationary. For example, it implies that the mean and standard deviation are constant throughout the duration. The charts on the right section of the dialog. The autocorrelations, ACF, and the partial autocorrelations, PACF, help you check for stationarity visually. If you click the Auto Detect button, @risk will automatically look for transformations of the data that produce stationarity. These include logarithms, first differences, and seasonal differences. Alternatively, you can ignore Auto Detect and check any transformations you want to apply. If the series is transformed, the transformed series will be fit by the various time series processes. Note that when you transform the data, the charts change automatically to reflect the transformed data. The Auto Detect feature uses a set of heuristics to determine good guesses for the transformations to apply to your data before fitting occurs. However, if you have knowledge of your data, you can override these guesses. For example, for our metal commodity prices, we will use a log transform with first-order differencing, which takes into account compounded returns, even if this is not the transformation set determined by the Auto Detect feature. This can be assumed, as such, since prices are retrieved from a relatively efficient market, where the assumption of adequate price formation implies that prices behave log normally, therefore compounded returns behave normally.